Good morning and welcome to our first of a series of seminars for SUSFERT, where we're looking at the next generation of bio-based fertilizers. Today we will be focusing on the components aspect, bringing components to products, and we'll introduce a number of distinguished speakers and guests to this forum. So I'm very happy we're joined not only from our location here in Turin in Austria with a group of participants, but also Europe and worldwide. So what we are attempting to do and combine in this next almost 2 hours is 5 years of research and innovation. So as a matter of fact, it's probably just half of that because we're focusing on the component side this morning. We will have another seminar later this year looking at the products to impact section. But in this next nearly 2 hours, we will be looking at a number of innovations that we have created over the past 5 years. As Bob Dylan sometimes said that the times they are changing, and so is the fertilizer industry. And as a result, many industry drivers are in motion, and we have a lot of stakeholders and actors within that value chain that are directing that change. So a lot of these key drivers are here today, and we will go through a number of presentations. We will start first looking at the fertilizer components and the excitements that we can generate of this. Do we have a presentation? Yes. Yeah, here we go. So first of all, we'll look at some of the components that we need to be excited about in the fertilizer world, followed by looking at the various components that we have for bio-based fertilizers. Then we'll look at the context of SUSFERT, what we're doing in terms of phosphorus and iron. Then we'll look at the power of the strain technology we've been developing. And a key component that is added to our solutions are the components of struvite as a phosphorus replacement. We'll be looking at enzymes and lignosulfonate solutions that we've been implementing, followed by the addition of siderophores to our SUSFERT solutions. All this will be wrapped up in a panel discussion, and we will then have the chance to discuss and elaborate on some of these aspects. A little bit of housekeeping. We're here in Turin in Lower Austria at the AIT, the Austrian Institute of Technology, and BOKU. So we're hosted here. This is an interactive seminar. Please put your questions into the chat. We will answer them either after the presentations if time allows. Otherwise, we will save them and integrate them into the panel discussion. And if we don't have time to address your question, we will follow up on that online. So please do visit our website for further information on that. So
start my video. Yeah.
All right. So today the components are the heroes. So over the past 5 years, we've looked at renewable sources for both phosphorus and iron. We've looked at adding probiotics as nutrient empowerment and availability. And we've looked at a number of coating solutions to allow us a controlled or slow release. Why are we doing this? We want to make an impact in Europe. So one of the things that we've set out as a mission for SUSFERT is to decrease the dependency on mined or imported phosphorus. We look thereby strengthening the circular economy, valorizing waste and byproducts out of the system. These in turn act as a soil improving characteristics and capacity, not only to reduce the soil contamination, but also reduce the fertilizer application as a whole. We're looking at solutions that improve the water holding capacity, a controlled release, and we're trying to embed all these solutions into our products. So in front of me, we have actually defined a number of products. We call this SUS kit, and so we have 9 prototype products that we are promoting, and I will demonstrate with one of them. So these are our hydrogels. They have been integrated together with probiotics and struvite, and I'll just kind of give you a quick demonstration on how this works. So we have a powder here, it's granules, and then we will see what happens during the course of the seminar, how our prototype solutions will develop. So I'll pour roughly the same amount of liquid granules in. I'll add some of the water. I think maybe it's even too much. So we'll be excited to see what happens to this. And in the meantime, I'm very excited to introduce our first speaker, Robert van Spingelen. So Robert, welcome. So Robert has more than 20 years of experience in the fertilizer industry.
Thank you, Michael.
And really looking at the development and marketing and implementation of new fertilizer solutions. So he has a long record in the regulatory affairs, and he's also the president of the European Sustainable Phosphorus Platform. Robert, thank you for joining us today, and I hand over to you.
Thank you, Michael. And thank you for the invitation to be here. Very nice to see all type of sustainable developments going on new things, on new items, and looking forward to that. Quick question, a presentation from where can I find it?
Here it is.
Technology. There we go. Yeah. So there we go. So we talk about next generation bio-based fertilizers. That's the topic here. And I talk about a few specific components, for enhanced nutrient uptake. And with enhanced nutrient uptake, it's also we talk about nutrient efficiency. And nutrient efficiency you can define in very different ways and different methods. I talk here about a few which are more slow release, and due to the slow release, it actually gives you a bit more nutrient efficiency. What am I doing? Yeah, I'm talking of where I'm working for RecyFert, which is a consultancy company. We focus on valorization of organic waste, as we call it. And of course, waste is not a waste if you can reuse it. Type of clients we're actually doing is biogas startups, fertilizer companies, and nutrient recovery companies. People that have a waste, for example, the biogas, they make biogas, but they don't know what to do with the digestate or less to do with the digestate. And that's what we actually are focusing on. Myself, more than 20 years experience in the fertilizer industry, development of new fertilizers, marketing of fertilizers, project development of organic fertilizer factories. So we've been helping with the design of a few organic fertilizer factories, specifically based on the biogas plants, regulatory affairs for EU fertilizers, and I'm the president of the European Sustainable Phosphorus Platform. So taking that further, I hope you can see this all. Yeah, that's better on the screen than on the computer screen. So what you see about nutrient recovery, you've got nitrogen recovery on the left-hand side, and you've got phosphorus recovery on the right-hand side. If you talk about, let's take the phosphorus recovery first. Yeah, the ones you can recover or the ways to recover is struvite. It's going to be iron phosphate or ammonium phosphate. It's going to be calcium phosphates, or you could use phosphoric acid. Yeah, and these are the 4 green boxes. And then you take the blue boxes, actually, okay, how are you going to do that? Yeah, so struvite is by precipitation of the orthophosphates, so the water-soluble phosphates, by adding magnesium, because normally phosphates, water-soluble phosphates, and ammonia or ammonium are already in the waste stream. By adding a little bit of magnesium, you're making a struvite. If you talk about the iron phosphate and the ammonium phosphates, they normally are going to get burned to an ash, in the sludge, or a spray dried as suspension, one of the two. And there is a new technology coming up, by Kemira and Wetsus, where they actually take a big magnet, to take the iron phosphate out. That's in an initial stage. They've done some trial work, on the different wastewater treatment plants, and that's also one of the newer technologies. Then you've got calcium phosphates, which you get from a thermal furnace, creating slag, incinerating acids dissolved in sodium hydroxide, sludge treatment of acids, and then precipitation, and incinerated ashes dissolved in hydrochloric acid, as well as in hydrothermal hydrolysis of sludge-driven acid treatment and the precipitation step. That's the way to get a calcium phosphate. And if you do a sulfuric acid, in principle, you use the ash, which you dissolve in acids to get a phosphoric acid. If you go to the nitrogen recovery, it's actually a few less products you could make. It's in principle, if we talk about ammonium, we don't talk about nitrate here, but pure ammonium. You can make an ammonium salt, or you could make aqueous ammonia. And if you talk about both parts of it, aqueous ammonia, you can get up roughly to 40% nitrogen. Ammonium salts depend on which ammonium salt we're going to make. Either going to be a liquid ammonium citrate if you use citric acid, where you can get roughly about 7% nitrogen in the liquid, or a liquid ammonium carbonate, which then has a 10% nitrogen, but you're not allowed, or it's difficult to use as a fertilizer because at a temperature of roughly about 20 degrees, the ammonium carbonate starts to deteriorate into ammonia and CO2. So it's a difficult product to use as a fertilizer. But you could use that, the ammonium carbonate, actually, if you do a next step in a fermentation reactor, you might be able to make a potassium nitrate out of it. So it could be a source, the ammonium carbonate, for a second step fermentation. And then liquid ammonium sulfate, or MSUL as I call it, with a 7% nitrogen. So taking that, you see all the characteristics of the recycling. And we start at the left-hand side with the volumes, the yellow box. With volumes, you've got consolidated volumes, which are ash-based, or fragmented volumes, which are normally sort of small, which is struvite, nitrogen recovery, and the hydrothermal sludge with acid treatment, because they are all done on location. The volumes getting out of these products are not large in fertilizer terms or fertilizer factory terms. We're talking about 10 or 20,000 tons per year. We talk here about a few hundred tons maximum to get out of a local part. So this is disadvantages of the recycling part of it. If you do the same on the feedstock distance mine, so how much miles do you need to make for that feedstock? In principle, the S you could do actually long distance because it's quite compact. It's got a high content, so you're able to move that. Short distance, in principle, is a struvite feedstock because struvite it's liquid, so you would like to have your factory close by to where it's being made. A sludge feedstock, because also over there you're talking about a liquid you have to transport, and that's the same with nitrogen recovery as a liquid. Ammonium sulfate, you don't want to transport that too far because then you actually it costs you too much money. So you try to find for these type of products, you try to find a offtake close by to the factory. And then talking about energy use, you've got the high energy requirements, which is concentrated liquids, because that costs a lot of energy to either evaporate water out of it or with membranes getting to a higher concentration, and also drying salts. For example, sludge, if you've got a wet sludge of about 30% dry matter, if you want to dry that, it's going to cost you quite a bit of energy, thermal energy, to get it to a dry product. If you talk about low to medium energy requirements, that's incinerating to ash, simply because if you incinerate, you actually create energy, you use the energy, the carbon that's inside the product, that will be as an energy source to burn the product, as well as precipitation of nutrients like you do, for example, with struvite. So taking on to the next step, if you talk about nutrient use efficiency products, we take about three most promising product groups. That's foliar nutrients, as a leaf application. That could be spoon-fed nutrients, yeah, so placed close to the roots, like drip irrigation, for example. You could think about that. And then time-release nutrients, which are placed to the roots. And if you look at the picture next to it, you see 3 different samples, yeah, of an untreated soil, a struvite, and a normal NPK. You see the difference in the root development, yeah, using the same NPK sum and levels which are inside that product of the right 2 versions. So taking that further, time-release components, struvite could be one of them, which is nitrogen, phosphorus, and magnesium, calcium phosphate, iron phosphate, which is iron and phosphate itself. Yeah, but the value of a plant nutrient could be limited because you only can use it under certain soil conditions. Otherwise, the plant is unable to actually release the phosphate from the iron component. Organic matter, yeah, in principle, organic matter is also a slow release component. You could put a lot of organic bound products in there, elements, nutrients that release by deteriorating the organic matter. And then the possibility, yeah, you could think about ammonium oxalate, which is slow release by itself. It's never been produced, by the way, yeah, but you might be able to do that. If you talk about spoon-fed components, it's actually salt or liquid ammonium sulfate. Yeah, we talk about as drip irrigation or as a spray. Ammonium citrate could be a possibility, which is nitrogen version, and then liquid concentrates. So you can see this. What I did is I tried to make a nutrient sum of the different components. Yeah, if you talk about, we start on the left-hand side, you see struvite, which is phosphate, which can go up from 60% P2O5 to 28% P2O5. As a nutrient sum for phosphate. So it's a very high nutrient sum product which you can transport also easily. If you talk about calcium phosphates, yeah, the calcium phosphates are actually quite low in their phosphates. And you get to 4 to 5% of the phosphates. If you talk about iron phosphate, yeah, it's similar like the struvite. You get from also the 15 up to the 28, depending on the purity of the product. And then we talk about, if we talk about the N forms, you could think about ammonium oxalate in a dry form, yeah, which you're able to get from 18 to 23%. Ammonium sulfate as a liquid, then you get to about 7-8%. Ammonium solid, nitrogen, you're actually going to 21%. And then aqueous ammonia, you talk about between 7 and 15% max, yeah, depending on the temperature you're actually using to make that happen. And to the end of my presentation, any questions?
Well, thank you very much, Robert, for that most thorough introduction and showing us some of the options that are available. I think we have a number of questions that have come in, but I think for time's sake, we will leave them for the panel, which, so thank you for now.
Thanks, Michael.
And now with great pleasure, Hurve Päivä Rakas Kari, I introduce Kari Ylivainio from Luke in Finland. Kari is a senior scientist at Luke. It's the Natural Resource Institute of Finland. So he's been looking at a number of optimizing solutions for both mineral and phosphorus fertilizers, looking at the organic phosphorus-rich side streams. And he's currently also coordinating one of our sister projects called Lex4Bio. And with great honor, I welcome you, and he'll be guiding us through some of the components for bio-based fertilizers in the EU. The floor is yours, Kari.
Thank you, Michael, and thank you for inviting me to this webinar. And I suppose you will turn on my presentation.
Yes.
Maybe I have to press something here. Yeah. Yes.
Okay, good morning. So I'm from Natural Resources Institute Finland, located in Jokioinen in southern Finland. And I will present some results from Lex4Bio project, which is a Horizon 2020 project started in June 2019, and it will run until end of May next year. And on this project, we are the main aim of this project is to optimize the use of bio-based fertilizers in agriculture, considering their agronomic performance and also environmental and safety issues. And here we are considering on these bio-based fertilizers called as BBFs. And the main starting material for these fertilizers are these nutrient-rich side streams, mainly manures, bio-waste, slaughterhouse waste, and sewage sludges. And on this table, you can see the nitrogen and phosphorus content of these materials at the EU level. And if these materials would be spread evenly across the agricultural land in the EU, for example, manure would provide 41 to 52 kilos of nitrogen per hectare per year. You can compare this value to mineral fertilizers in which we are producing 63 kilos of nitrogen per hectare. And from manure, manure provides phosphorus roughly 10.5 kilos as compared to 8 kilos of mineral fertilizers. So from these figures, you can see that these are very important source of phosphorus and nitrogen in agriculture in Europe. So if you go to the next slide. Here we have a European map of manure-based nitrogen and phosphorus. And as you can see, one of the problem is that they are unevenly distributed in Europe. So this shows how much nitrogen and phosphorus originates from manure. And highest amount of these nutrients are, of course, formed in regions where we have a intensive animal production, mainly in Western Europe, where the nitrogen and phosphorus originating from manure is much higher than actually needed by the crop. So we should be able then to transport these nutrients to regions where is actual demand for these nutrients. Next slide. And if we want to produce recycled fertilizers from these side streams, and now we are talking about CE marked fertilizers, meaning fertilizers that are indicated in fertilizing products regulation, and these can be then transported across Europe, and there is no restriction for their transportation. And this fertilizing products regulation sets a limit for these components that can be used for producing fertilizers as such. For example, sewage sludge-based material after digesting or composting cannot be used as a raw material for recycled fertilizers, especially for these CE marked fertilizers. There's also a limit for nutrient concentration that needs to be achieved, and also from safety aspect, there exist limits for harmful heavy metals, which cadmium is the most important ones. And here on this figure, you can see some of the fertilizers that we have been tested in Lex4Bio. So depending on the starting material and production technologies, various component material categories exist among BBFs. So this is just a small set of fertilizers that we have been tested in Lex4Bio. So we can change the slide. So in Lex4Bio, we selected a total of about 40 nitrogen-based and 40 phosphorus-based BBFs that were screened in Europe, and some of these were also obtained outside Europe. Majority of these nitrogen-based fertilizers were animal byproducts or food industry byproducts. And especially when we were testing these on field trials, of course, we wanted to have such fertilizers that had a high enough nutrient concentration, so the transportation costs wouldn't be that high. For phosphorus, the main components were precipitated phosphate salts like struvite that was mentioned presentation before, or then thermally treated BBFs like ashes and pyrolyzed material. Next slide. Here are the nutrient nitrogen and phosphorus concentration of those BBFs that we were testing on field trials. And as you can see, although we have call them as a phosphorus fertilizers and nitrogen fertilizers, these recycled fertilizers also contains other nutrients than only phosphorus or nitrogen. For example, these phosphorus-based BBFs, they contain also some of them quite high content of nitrogen or potassium. And the same goes with these nitrogen-based BBFs. Many of them have a quite high phosphorus or potassium concentration as compared to these mineral fertilizers that commonly contain only those target nutrients. In phosphorus fertilizers, only phosphorus, or then on these mineral nitrogen fertilizer, it commonly contain only nitrogen, if it's not NPK fertilizer. And then the next slide. And then if we look at these phosphorus-based fertilizers, the solubility of phosphorus can vary considerably among these fertilizers. Water-soluble phosphorus that is commonly considered let's say, of course, it's the most bioavailable fraction of these fertilizers, and this water-soluble phosphorus content varied between 0 to 92% of the total phosphorus among these fertilizers. And then the least soluble phosphorus fraction, this acid-soluble phosphorus content, it was up to 95% of the total phosphorus. So there exists a great variation in chemical composition of these fertilizers. And in some fertilizers, they contain also quite high share of organic phosphorus. Although in most of these fertilizers, inorganic fraction was the main source of phosphorus. Next slide. Carbon concentration of these fertilizers varied also greatly. Lowest carbon concentration was, of course, in ashes and precipitated BBFs like struvite, and highest one was found from pyrolyzed BBFs. And it was in some fertilizers it was more than 50%. So the total carbon content was more than 50%. And of course, depending on this processing method, how these fertilizers were produced, this carbon stability may vary among fertilizers. So this will have a great effect how long the carbon will stay in soil after it has been spread. And this is because growing conditions across Europe vary, so it's important to, in some cases, to especially in southern Europe, to have stable carbon in soil. From these heavy metals, cadmium concentration were most often below the limit set by the FBR. And on this left-hand side, there is a cadmium concentration in mineral phosphorus fertilizers. And many of these BBFs, cadmium concentration was even below those values. And in some cases, it was 0. Lowest one found from precipitated phosphorus sources, including struvite. Next slide. So as a conclusion, this chemical composition, it varies a lot among these component materials, as well as then phosphorus solubility. And from the safety aspect, the harmful heavy metal concentration were most often below the limit set by the FBR. And nowadays, the carbon sequestration is an important issue. So depending on these production technologies, these PBFs may provide a way to increase recalcitrant carbon pool in soils. Thank you.
Thank you very much, Kari. I actually have a number of questions also looking at the transportability and the economic rationale behind all this that you addressed slightly. I will keep that and wait for that for the panel discussion. In the meantime, it's with great honor to introduce our scientific coordinator for SUSFERT. We've just heard what Lex4Bio is doing in terms of the fertilizer innovations. Now Günther Brader is joining me up here from AIT to talk about the SUSFERT activities and innovations. So Günther has been, he's in the field of molecular biology. He's a senior scientist at AIT, and he spends most of his time looking at the micro interactions and looking at genome characterizations, comparisons, safety aspects for fertilizers. Günther, the floor is yours.
Thank you. Thank you, Mike. Can I have a presentation, please? Thank you. Okay. Yes. So as Mike pointed out, today we will focus on components in our project. But what I want to do first is to wrap up a bit what SUSFERT is all about and what we are aiming at the SUSFERT project. And then in the next couple of presentations, you will hear about each of the components in more detail. So the SUSFERT project is aiming at developing multifunctional fertilizers for both phosphate and iron supply. The project has contribution of large industry partners, SMEs, and research organizations like AIT, the University of Antwerp, and the BOKU. What we are aiming here is not only to use or to increase phosphate using and reusing phosphate, but to show that it is possible, and that's one of our crucial aims, that it showed that it's possible to introduce that into current fertilizer solutions so that there will be a good entry into the market. Next slide, please, or can I change it myself? Yeah. Okay, so what would be the context and the objectives of our project? So first of all, as you have heard before, some of the crucial nutrients are, of course, critical resources and are largely imported into the EU, both in terms of energy use and in point of import need. Phosphorus is one of the major critical resources. It's 90% imported. And this dependency of resource-intense fertilizers need to be reduced and need to be put on a longer perspective. Another important aspect is that quite large amount of nutrients is actually not used because it's not available at the right time. Plant needs fertilizers in their development in different amounts. At their development, a lot of it is washed away and or is bound into the soil. And with certain solutions, we might be able to reduce this loss. So, and SUSFERT does that by using bio-based and biodegradable coatings. We will hear about that from Renate later on. then using bacteria, probiotic solutions to increase nutrient availability. We will hear this from Christine in a few minutes. And yeah, the use of the already mentioned struvite into current fertilizer solutions. We will hear this from Mark in more detail later on. Sorry about that. Yeah, okay. So, and the aims of SUSFERT, as mentioned already by Mike, but as these are, of course, important, I want to reinforce and repeat that, is to decrease the dependency on the mined phosphate, and our aim is to reduce this by 40%, strengthen circular economy and valorizing waste stream, as for example, byproducts, to be more precise, for example, in organic fertilizers. We want to reduce soil contaminations by using siderophores produced by fungi. We will hear this from Martin later on. And we will also want to strengthen the rural areas and local value chains, and especially also demonstrating green technologies, as we have actually a startup integrating in our project dealing with nutrient jail solutions based on lignin. And just to very briefly mention the trials and highlights what we have been doing so far. We are in the 5th year of SUSFERT, of course, and we have already 4 years of field trials and having another year of field trials going ahead. We are doing field trials in maize, tomato, oranges, kiwi, and grapevine, and I hope I mentioned every one of those cultures we have been using. We are aiming in producing granules, microgranules, liquid and organic fertilizers, and soil improvers. Having lignin-based water and nutrient solution, as already mentioned, the Nutri-Gels. Iron fertilization by both an organic fertilizer product, we will hear also later, and fungal siderophores, and aiming at combination of microorganisms, struvite, classical NPK, and lignin-based coatings to really having a classical fertilizer product, but with higher sustainability. And with that, I'm already almost finished. I just want to give 2 slides where I show our contacts from Mike and me, and we want, in lieu of everybody, I want to give an acknowledgement slide. So this acknowledgement is, of course, for all the SUSFERT presentations valid, and we show it once here that you all know this as well. So thank you very much for your attention.
Thank you very much, Günther. We'll hear a little later from Günther again on the panel. In the meantime, we move forward, and I welcome Christine Dietl she's Head of Regulatory Affairs for Habitat. She is on the project looking to understand the factors that influence the efficacies of our microorganisms. So glad to have you here with us virtually, at least, Christine. And she will speak about the power of strain technologies. Christine, the floor is yours.
Thank you, Mike, for your introduction. My name is Christine Dietl, and I'm working for Habitat. It's a company that is located in Berlin, Germany. And we are a producer of beneficial microorganisms. And as Günther told you, we are our part in the project was to develop microorganisms. And now, as you know, please, could I have my presentation? Thank you. Okay. As you know, on Earth are living 5 times 10 to the power of 31 bacteria, a 5 with 31 zeros behind, an incredible huge amount. Of course, environmental microbiologists estimate that less than 2% of bacteria can be cultured in the laboratory, but this only reduces the number to 10, 30, high 30. So how to find the Mr. Right for our project? At the beginning of our project, we have thought a lot about screening and what microorganism would be the best solution. We thought about key functions, technical properties, where to look for good candidates, and which properties would be cut-off criteria. As Mike and Günther told you before, the project was aiming to solve the phosphorus and iron nutrition problem while reducing the input of non-renewable fertilizer resources. We had the goal to mobilize phosphorus from poorly plant available sources like rock phosphate, and also to show the combination with waste materials such as struvite. As a preset condition, we choose to look for microorganisms that are on one hand able to promote plant growth and on the other hand are suitable to be formulated in a fertilizer product. The most important characteristics of our wanted Mr. Right were its resistance against chemical and physical impacts such as high salt conditions or high temperature. And finally, it had to be a nice guy, not toxic to plants, humans, environments, or animals. Now I would like to introduce you a little bit to the benefits that microorganisms are able to provide in combination with fertilizers. It is known that they help the plants to acquire phosphorus and iron from poorly plant available sources. The microorganism usually is colonizing the plant root or the rhizosphere and produces enzymes like phosphatases that are able to mobilize phosphorus, or chelating peptides like siderophores that make iron plant available. Other tools of the microorganisms are to change the pH by exudating organic acids, shift the soil community so there are more the ones that are known to be beneficial, and last but not least have the advantage to produce volatiles and phytohormone-like compounds that stimulate plant and root growth. In the project, we had 3 phases for the probiotic development. We started with the big strain collection of RET and Abitep and evaluated these for phosphorus and iron mobilizing abilities. This was the starting point for our demo project. We looked for the candidates that were easy to propagate and choose different bacterial genera. By RET and BOCO, several greenhouse trials took place to figure out the best candidates for the combination with fertilizer compounds. In the meantime, at Abitep, we tested the strains for their chemical and physical stability, developed production processes, and tried to find stable formulations to be delivered as a raw material for fertilizer production. From over 1,000 candidates in the beginning, only 30 strains came into the NERA focus, which were tested in greenhouse trials. These efficacy trials that were performed on tomato by RET showed clear differences between the ability of strains to mobilize phosphorus from calcium phosphate. In the graph, you can see the fresh weight of tomato plants grown under different fertilization. The first column is the control with no phosphorus treatment. Next is a full fertilized control with potassium dihydrogen phosphate as source. Next is a control with calcium phosphate as phosphorus source that is poorly plant available. And the other columns are the candidate strains together with the calcium phosphate as P source. One of the promising candidates, the strain is shown on the right side. As you can clearly see, the plant growth with calcium phosphate in combination with the microorganism is nearly as good as with the plant available phosphorus treatment. And also much better as with the calcium phosphate alone. To prove that the effects can not only be shown for tomato, also corn was used as a test plant. As you know, corn has a great appetite for phosphorus in its youth and makes it clearly visible if it's starving by showing reddish leaves. So it is a perfect test plant for phosphorus availability. In this greenhouse trial, the phosphorus deficiency symptoms have been evaluated. In the graph, you can see different bacillus strains in combination with rock phosphate as P source. In the experiment, different phosphorus sources were used as control. Rock phosphate and calcium phosphate as poorly plant available P sources, and super single phosphate as standard fertilizer. The deficiency symptoms have been evaluated, and a high score means phosphorus deficiency, and lower scores less symptoms of phosphorus starvation. The evaluation makes it visible that some of the strains had a good potential to mobilize phosphorus from the poorly plant available source rock phosphate. Out of all the tested strains, we selected 3 candidates for further probiotic product development that included the fermentation process, scale up to higher volumes, look for the downstream process development, and to find the best and stable formulation to combine it easily with fertilizer compounds. With these products, several prototypes of fertilizer were tested. How this was done, you may hear in the next presentations. Thank you.
Thank you very much, Christine. Lots of exciting stuff, and I hope that we'll get a chance. We've got some questions coming in, so please stay with us for the panel, and we'll address some of the questions we've received directly to you. In the meantime, I want to introduce Mark Spieler from the University of Antwerpen. We've heard a lot about the topic of struvite earlier, and we will continue to hear more about struvite. So I welcome Mark to join us to really talk about the contribution to the circular economy of struvite. Mark, good morning, and the presentation and the floor is yours.
Good morning. Thanks for the introduction, Mike. Good to be here, and finally, after so many years, present some of the results of our work. I'm clicking, it's not yet moving.
Patience, young man. It might come. There we go.
Okay, here we go. Yeah, very good. So I will present a little bit work that we have already published a couple of years ago on struvite, but here we'll specifically ask the question whether struvite can contribute to the circular economy. Maybe there has been, Robert has already introduced struvite very well and speakers before me, but just a very short introduction to why is phosphorus and struvite important. So, of course, struvite being phosphorus mainly. Phosphorus is important in the circular economy because we are having this looming resource shortage as a non-renewable resource, phosphorus. And on the right-hand side, you see one of the most famous graphs, I suppose, when you think about phosphorus from Cordell 2009, talking about peak phosphorus, so the point where the phosphorus mining and resources peak and then decline to a terminal point. Well, we can debate about the specific dates and decades when we will reach a no phosphorus or a peak phosphorus, but it is upon us and it's coming. And because of that, the EU has declared phosphorus a critical raw material, to my knowledge, by 2014. And one aspect also important of phosphorus for the circular economy is that it's comparatively easy, I would claim, to recover, as it has no gas phase, it's not volatile like, for instance, nitrogen. So where it is, it stays. It's a true mineral that precipitates out, for instance, etc. And that's exactly what struvite is, a precipitant of phosphorus, and more specifically, as already introduced, of magnesium ammonium phosphate, MAP sometimes called. So it's a real crystal, has a crystal structure. That's also what you see with the 6 waters here included in this formula. It has a rather high phosphorus content of 12.6%. And there is a small error here. I took 32.6 as the phosphorus pentoxide. That's of course not correct. It's more between 28 and 29%. And this is more a value you would expect for phosphate rock. And indeed, this is refined phosphate rock, that is. And this is indeed means that the theoretical P content of struvite is very similar to that of phosphate rock. So question is, could we replace our mined resource, our limited resource phosphate rock with struvite, for instance? Is that an option? And of course, also as shown or this mentioned already, phosphorus has been proven, or struvite has been proven multiple times to be a good slow release P fertilizer. If we now look at where do we get struvite from, was already a little bit mentioned, but we did the study in 2019. We gathered data on pilot sites and full-scale sites in Europe where you can get struvite from, and we found that most of it originates from municipal wastewater, so sewage treatment plants, not to be negligible fraction also from potato processing, where phosphorus is added to avoid oxidation of the brown color of the potatoes. And that seems that's nice, but if you look at the numbers, so you see here the numbers in tons P per year, between different, depending on the assumptions we are taking, between 1,000 to 1,300, a bit more tons of P a year. This is much less than 1% of the fertilizer imports, more like 0.5%. So it's really small what we currently recover in terms of phosphorus struvite, and to replace this in agriculture as a fertilizer. So there's a lot of growth potential. I can say this already here now. Maybe as an interesting side note, as a fun fact, is that struvite has actually nothing much to do with producing a fertilizer. No, these wastewater treatment plants that I just talked about actually implemented this struvite precipitation as a way to remove phosphorus and to avoid, for instance, on the right-hand side, pipe blockages that they're getting when struvite precipitates spontaneously in their pipes, and to increase their dewaterability of their sludges, which increases, or which is a big cost item for these wastewater treatment plants. Which leads me directly to a bit more zooming in of where struvite can be produced. There are 3 types. I will go over this relatively quickly. One thing they have in common, all struvites that we researched at least are produced after anaerobic digestion. There might be some struvites produced on urine, for instance, but after anaerobic digestion, because it releases the phosphorus in a orthophosphate PO4, so that you can then precipitate out. And the first thing is, so on a digestate, it means a mix of solids and the liquid streams of nitrogen and phosphorus, the dissolved components, the inorganic components. By adding magnesium, you can precipitate out struvite. That's option one, which you call digestate. But we can also precipitate out struvite on a liquid fraction of the digestate, the dewatering liquor, so to speak. That is then what we call struvite 2. Again, similar process. We add magnesium and we get struvite and nitrogen out of it. Nitrogen in about 5.6%. And the very final way of precipitating struvite that we researched is from anaerobic digestion, a UASB as well, which is a type of different anaerobic digestion from the agro-food industry. And that's type 3 struvite, as we call it, as you will see in a moment. Very quick statement about what we did. So the aim was to compare the struvites that we gathered, 25 gathered 25 struvites, compare it to the EU fertilizer regulation that came into force in 2022, so the new one. We did a full physical, chemical, and biological analysis for that, which was rather innovative. And we did also, with the help of Boku, some pod trials. And now I dive into the results. You don't need to look at all these complicated graphs because we have 25 samples, so they are rather detailed. But the key message for you is always on top. So here the key message on the P concentrations, and you see also the N and magnesium concentrations, is that they are all pretty good, pretty high. All but one sample, the one down here from Anfos, meet the criteria of at least 7% P in the dry matter. Most of them are above 10%, and some of them even exceed the theoretical limit. One reason why, for instance, some of these struvites have a very low concentration of P is because these are the early struvites and they're not actually made to recover P, but they're made as a process improvement. If you look also at the organic carbon content, which is also regulated, it must be below 3%. We see that in most cases, or nearly all cases, in 22 of 25, we have an organic carbon content that is below the limit. So it's good. Again, some of the Anfoses and some phosphates that are more slurries exceed this. Heavy metals, always an issue, but we heard it earlier already that this is actually not a non-issue, and so it is for struvite. There's not really a big issue here if the fertilizer limits are on the left-hand side, and the actual detection limit, or what we detected, is here in these other bars. So you see these bars never come near any of those regulated limits and heavy metals that we have. Notably is maybe zinc, that is a bit elevated. Of course, this is from gutters and drains where we collected. As for fertilizers, cadmium is important, but also here we don't see any issues for struvite specifically. So that's a good thing, thumbs up. We did also some struvite fingerprinting, a combination of the elemental analysis and in mineralogy we did. The good news is the majority of what we found is struvite. However, we found also a large fraction of amorphous components in our analysis here on the top bar. So some, even 50% of the struvites are amorphous. So we cannot say what it exactly is here. And we also, in some struvites, we find a large fraction of sand that's also mixed into the game. So silicium dioxide, that also is some contaminant. And then of course the slurries, you see a little bit more contamination here. What we also did, and it was rather innovative, we want to not just see what's physically or chemically present in terms of P and N and magnesium in there, but also can we actually apply it and use it on land? Huh? And you see here a picture of two struvites that we collected, one on digestate, which is more orthorhombic, more long, and the liquid fraction struvite. So there's type 2 struvites that are really nice and round shaped. So almost a granule like we would expect it in agriculture. And indeed, if you look now, well, why is this important? Maybe first, we need these granules, these nice round granules for different applications. So these smaller granules between 1 to 2.5 millimeters, we can apply in rows. The somewhat bigger ones, we can use them for spreading a bit further. They fly nicely, as you can see here below. And so we did this analysis, granulometry, a difficult word, of these struvites. And what we found is a little bit suboptimal, if you want. We can say that most of the struvites are more likely to be applied in rows as these microgranules that we had. So most of the struvites are either very small to 2 millimeters, and a smaller fraction is above 2 millimeters. But we also see that we have some struvites that can be, here on the right hand side, very large in size. So it is physically possible to make a struvite that is more orientated towards a market. So there's just some more development going on, and there's certainly still applications enough for also smaller grains, as I will come to. One of my nearly last slide for you is actually our tests, our trials with pot tests, tomatoes. And well, you see here, our key message is that actually we don't see a difference between our struvites and single superphosphate, but we definitely with struvite are better than phosphate rock, to be expected. We also proved slow release capacities, but I don't show these results. In conclusion, yes to struvite in a circular economy. It is a good stuff. It works. It is of good quality overall. As we have seen, we are rarely failing the legal limits that are prescribed by the new regulation. However, there is an issue of the size of the market that we currently have. Only currently 0.5% of nitrogen phosphorus fertilizers in the EU could be replaced. But if we take everything into account, we could maybe go up in the most optimal scenario to 13%. And future application possibilities, of course, in and beyond SUSFERT, we can use struvite to blend it with NPK fertilizers. We can apply it in growth media, so more high-end and specific applications, especially also for smaller granules. And we could see to how we could integrate this as a P-rock alternative in complex fertilizers. But there are some challenges here that we're still researching. If you are interested more and want to know more about these results, you can access them here. And here also all of the many people that contributed to this work from all over Europe nearly.
Thank you very much indeed, Mark. That was most compelling, and it shows the potential of struvite. With a number of hurdles, but lots of potential and opportunities there. There's a few questions. Again, we'll try to rank them up to the end, so please stay with us. In the meantime, I want to invite the first of our dynamic duo. So it's Niki Schweiger from SAPI. He's a chemical engineer looking at the biorefinery processes. And Renate, who's joining us here live, she's a senior scientist at BOKU, the Institute for Environmental Biotechnology. And they've been looking at lignosulfonate coatings and enzyme technology. So this is our winning team in SUSFERT, and we're looking now at enzymes and lignosulfonates as the winning team for the bio-based circular economy. Renate and Niki, I think Niki, you will commence.
Yes.
Wonderful.
Thank you, Mike, for the nice introduction. So starting and waiting to get my screen in. Welcome everybody here from the SAPI site in Gradkorn in Styria, south of Austria, close to the Slovenian border. Yes, thank you, Mike, for the really kind introduction. And I would like to start with our title, NextGen Bio-Based Fertilizers from Components to Products. And we are here definitely enzymes and lignosulfonates, a winning team for bio-based circular economy. And I think Renate will then give you a better insights on the, a little too fast. Yes, we'll give you insights on how enzymes will interact with lignosulfonates. But first of all, I have to introduce SAPI, South African pulp and paper industries. So we have 10 mills in Europe, 5 in South Africa, 4 in North America. And today I have the honor to represent a company with close to 13,000 employees, and we are really spread all over the world. So we have customers in over 150 countries, and of course we have employees in 20 countries. So, but why is SAPI here? As I already stated, SAPI is home-based in pulp and paper industry, and this whole industry is turning into much more biorefinery applications. In Europe, we have roughly 10 mills, and out of those 10 mills, 4 are integrated pulp mills, and we are doing a special sort of pulping. It's so-called sulfite pulping. And this sulfite pulping is having a special mode of operation, I would say. It's not the standard craft unit operation, what is used in most pulp and paper protection sites all over the world. What we are doing is we use magnesium and SO2 to make lignin into so-called lignosulfonate and make this material water soluble. By doing so, we gain cellulose and the hemicellulose, which is stuck on cellulose for our paper protection, what is not just graphical papers, it's also packaging, nanocellulose, and so on. But as a side stream of these pulping processes, we have in our 4 SAPI mills, we generate a lot of those so-called lignosulfonates, and nowadays they are mostly used for incineration to close our chemical recovery recycle process in all our mills, but we are highly interested to give those compounds new applications. At the moment, we have applications in concrete admixture or in paints as dispersing agents and so on. But our challenge is to develop new applications for these lignosulfonates without impacting the energy supply of our mills. And with that slide, I will hand over to Renate Weiss, and she will explain how she is using lignosulfonates from SAPI to make new products for bio-based circular economy.
Thank you, Niki. Thank you again, Mike, for the nice introduction. So I want to show you how we produce polymers from lignosulfonates by utilizing enzymes. So we have developed a method for polymerization by NACase and MTL. And with this polymerization, we create a lignin polymer, as you can see. And what is very important here, the polymerization leads to an increase of molecular weight and viscosity. And with this, we come to a material that then can be used for various products and applications. And one of them is the use in coatings for fertilizers, as well as a water-holding gel. So, but what is really important in this case, if we produce this material, it really has to be compatible with plants and with the environment. So it has to be tested for safety. We performed in vitro testing on various model plants like iceberg salad, tomatoes, grapevines. And here I show you the results for the iceberg salad, where we see that the germination is not affected by the lignosulfonates. Also the growth and the plants themselves are not affected by the lignosulfonate. There is no negative effect. Also the soil pH and everything is stable when introducing polymerized lignosulfonates in soil. So here are some results of the soil improver. This is, we developed this during the SUSFERT project. It's also in the SUS kit that will be presented. And here the point was we combined certain products of the SUSFERT project, the calcium carbonate granules, which were from Roulet, our coating that we developed to stabilize these granules and don't have as much roll-off during the storage and the application. And in addition, we added Habitat's microorganism, in this case Bacillispores, to enhance the nutrient uptake of the plants. So here in this graph, you can nicely see how the addition of the microorganisms improves the plant growth, as well as the addition of the calcium carbonate. As you can see, when no calcium carbonate is added, we have lower plant weights as compared to the variants where calcium carbonate is added. And in addition, the best variant is when a microorganism is introduced into this system. This we could also show in field trials that were performed on lawn as well as on potatoes, where we showed better root growth, root structure in the plants, and higher cut weight of the grass. Yes.
Thank you very much for that, and Nikki. It shows very clearly the effect of lignosulfonates in our fertilizer application. And so I think there's a lot of opportunity and chances for further advancements. We will advance ourselves now. We'll go from lignosulfonates to the next big category. We're looking at the iron supply. And with me here is Markus Ohmann. He's a technical biochemist. He spearheads, works for ARIC, which is the Agrana Research and Innovation Center. He's the head of the Department of Microbiology and Biotechnology. And he's now also the head of the Fruit Technology and Life Science. And I do believe that Agrana, for those who may not know, is an Austrian giant for fruit, starch, and sugar. And I do believe that every second fruit yogurt has passed your desk, Marcus.
More or less, yes.
So there we have that. In combination with Marcus, we will be joined from Slovenia by Martin from ACS Bio. He's head of business development there, and he's been looking at upscaling some of the activities that we're doing in terms of the iron supply. And we had the privilege to actually inaugurate the fermenter in Slovenia a couple of weeks ago, where we're producing the siderophore, which is actually one of our SUSFERT prototypes as well here. So without further ado, I hand over to the Iron Men of SUSFERT. Marcus.
Thank you, Mike. Okay. Yeah, when we talk about bio-based fertilizers, I think we also have to talk about plant diseases and how different add-ons for fertilizers can overcome these diseases. And one of the very famous one. Okay. Rechts. Yeah, it works. Yeah, one of the most famous diseases for plants is iron chlorosis. You can see here on this picture grapevine leaves and in different stages of iron chlorosis. This means the more severe the disease is, the more yellowish are the plants, the leaves of the plant. This means because. Okay, does it start the video? Start video. Start. Yeah, start.
Start. Yeah.
Yeah.
Okay.
This means that the plant is not able to produce chlorophyll anymore because of the lack of iron. This is a very severe problem, especially in Mediterranean countries and in lime-rich soils with pH above 7. The reasons are two different ones. First of all, at a very high pH or a pH in an alkaline range, the iron is bound as insoluble iron hydroxide. So this means the iron is really tightly bound to the hydroxide and cannot be taken up by the plant and used for chlorophyll production. And the other reason is in high lime or lime-rich soils, the bicarbonate affects the iron uptake of the plant and its translocation within the plant. What are the measures which can be done to overcome this problem? First of all, there is the farmer. The farmer can do the ventilation of the soil, which means that it expels the CO2 out of the soil, and then the soil gets more air in and the pH drops, and then the plant is able to use the iron which is in the soil available. Or the farmer can also use an artificial iron supply. This is, for example, sequestrin 138 iron. This is a very common one, which is used by the farmers if they see the first hints of iron chlorosis on the plants. It is allowed at the moment also for organic farming, but of course it's not really wanted because it can accumulate in the soil. It does not degrade naturally, and it cannot be reused. So once there and used, it stays there forever. And it means that as soon as there is an organic alternative on the market, farmers have to use that instead of this artificial sequestrin. And what can the plant do to overcome iron chlorosis? Plants are producing organic acids and put them via their roots into the soil to decrease the pH. If the pH decreases, the bound iron to the hydroxide is released, is free as an ion, and can be uptaken by the plant and used to chlorophyll production. And another way is plants can produce siderophores. This magic word we have heard a lot, many times before. Siderophores then also excreted by the roots into the soil to complex iron ions. So what are siderophores? This is a Greek word which is meant as iron carrier. They are small oligopeptides between 300 and 2000 Daltons, and they build complexes with metal cations, especially with iron 3+ ions, but they can also use different other ones like zinc and so on. So they ensure the iron supply of the organism, and they are not only produced by plants, but also by bacteria, by yeast, by fungi. So now this is where the Agrana Research and Innovation Center comes into the game. We wanted to know how we can produce these siderophores in a way that we have it in a certain amount, which can then be added to another fertilizer, for example, spread onto the field and ensure the iron supply of the plants. First, we did, of course, literature research, and we found some different organisms, microorganisms, which are able to produce siderophores, which can be also uptaken by the plant, even if it comes from a fungi. This was, for example, the fungus Neurospora crassa. It's in a filamentous fungus, and we tried to ferment it. And we also could get some yield of the siderophore, which is called coprogen, with the fermentation, but there were some limitations. First of all, the yield was quite low, so we needed a lot of fermentations to get a sufficient amount to do some fertilization trials. And for all of you who has done fermentations, you know that fermentation of a filamentous fungus is very complex and very hard to perform. So we wanted to change this organism to another one, and we found in literature a yeast which is called Rhodotorula mucilaginosa. You can see it on the right side, this very nice red microorganism. And this is producing the siderophore rhodotorylic acids. And this is also able to be uptaken or used by the plants as an iron supply. The advantage was we had a much higher yield of this siderophore, by 100 times higher, and this fermentation of a yeast is much simpler and much easier compared to a filamentous fungus. Yeah, now I want to hand over to Martin Kauschek, who did in ACS Bio the upscaling of this rhodotorylic fermentation. Thank you.
Okay, thank you, Marcus. I'm gonna start where Agrana Arik stopped, and I think this is a great example of how we can collaborate together and bring new technologies, new products on the market. And what we are doing at ACS Bio is basically producing new technologies using microbes and using precision fermentation. We are based in Ljubljana, Slovenia, and we have a platforms for development of new technologies from, let's say, from strain up to commercial demonstration, and then also production. And maybe I would like to start with a little bit of insight how to develop a new bioproduct and what is usually perceived. So you have an idea, you look into the literature, maybe build upon the knowledge that already exists, but then optimize this product towards a more mature technology using the design, build, test, and learn cycle. And in each cycle, you optimize one aspect of the technology, and at the end, you come to a final product or final technology, except that we believe there are still quite some additional value creation steps that needs to be done between this, let's say, prototype and the final product that is then put on the market in a way that is needed for it to be successful. So in the course of SUSFERT, in the course of iron deficiency product development, what we did is, let's say the left part was mainly done by Eric, and we took it from there and made the process more effective. We scaled the process, optimized the downstream processing so the final formulations can be made, and of course, when going towards the markets, also the regulatory steps will have to step in, and in that way we will come up with a final product, final solution. Really, this is a team effort that we are doing, and many different aspects are needed in order to come to a final product. So in that sense, for example, Arik started and found this beneficial yeast that is producing iron chelator, rhodotorolic acid, that is released into the fermentation broth when the yeast grows, and then we have to basically go into two different ways of optimizations. In one way, we have to see the effect of the rhodotorolic acid through greenhouse testing, field trials, and then also final formulations, and that has been done by AIT, also Eric in the past, and also Ruli and Timak Agro in the SUSFERT. What ACS Bio has been doing is basically optimizing the efficient production technology so that we can also produce in the amounts that are needed then to go to the market, and before to test everything, and also of course to do that in a economical manner so that we can then at the end use the product in the field and prevent iron chlorosis. So going a little bit further into our activities in the SUSFERT project, we optimize the media conditions so we can use glucose or side streams of starch production, but also some others. We optimize the cultural conditions for production, so increasing the productivity so that the fermentation is not too long, and that we can produce enough of the siderophore, but then also optimizing downstream processing so that we can have in the end efficient and cost competitive formulation that can be either in a liquid or a powder form, and finally we basically made a scale up from a small lab scale of let's say 100 milliliters of the broth that was done in the shake flask through scale up to 6.5 cubic meter fermentation, and in that way we proved that the industrial process can really be made in a industrial way, and also produced quite some amounts of concentrated siderophore that is being tested then in the field trials and in the greenhouse trials. So as Mike also mentioned before, in the course of SUSFERT, ACS Bio also invested in optimization and let's say expansion of our fermentation facility. We added new 6,500 liter fermenter that is intended for scale up and the production of the siderophores, but also other ag biotechnologies. We have expanded the downstream processing equipment for biomass separation, concentration, and formulation, so that we can also produce different kinds of final products, and in that sense we can complete our let's say development of different microbial technologies, and not put only the siderophore on the market, but also think about other microbial technologies in terms of plant growth promotion, in terms of biofertilizers, and also biopesticides that can be produced in this new and expanded pilot facility. So with that, thank you very much for coming to the webinar, and if you have any questions, I'll be happy to answer it now or later.
Well, now is the time for not just the questions to you, but to all of us here. So I have a number of questions that have come in. So I'll some of them, Kari, you're still there. We have the first question came in regarding your last slide, that the colors of the various components reflect the colors for NPK. I take it that that's correct. And then a follow-up question is, if you did you test how long the seed stays in the soil, Kari?
Yes, hello. Would you repeat the question, please?
Yeah. Did you test how long the seed stays in the soil? The carbon.
Oh, the carbon. Well, we haven't done that kind of incubation experiment, but I think that there is some mineralization studies going on at the moment regarding these fertilizers, but I do not have results on my hand at the moment. So,
okay.
But it's clear that if you are pyrolyzing carbon-rich material, the carbon is much more recalcitrant against mineralization, so it will stay there longer.
Right. So then I'm also joined here by our panel. Maybe we can get them to zoom them in. So I have a question for you, Robert. So we heard a lot about struvite and also the price of struvite. Now, is the price right? And how do we, how competitive is the pricing in terms of the attractiveness of struvite?
Yeah, attractive pricing. I always say pricing depends on the quality of the granule. Yeah, and what you've seen, what Mark Spiller was showing, if it's a granular product, yeah, from the waters, derived from the waters, or if it's a spontaneous reaction where you get a crystalline product. Round products most probably are going to be sold better at a higher price, and I think also what you could see in this time for the Ostara product, the struvite, which is actually most probably shown in most of the round granules in the presentations. Yeah, I believe they're sold out for a price which everybody knows it's higher than everyone thinks it is. So price is an issue, but apparently people are buying it. Yeah, and they see results out of it. It's apparently far better for the price than the SSP product or MAP product.
Right. So that's actually something we've seen here. I have a question here. Oh, please.
But that has changed recently, hasn't it? As far as understood from the discussion with Mark, a couple of years ago, let's say 5 years ago, when we started our project, actually, that was not the case. Then struvite was basically staying on the shelf.
The problem with struvite, and that's still the case, is you need to try to get that CE registration. That's where Ostara is working on the moment. Yeah, to get that CE with the CE registration. The fact that the new legislation came in 2022 actually opened up a whole lot of possibilities for the struvite, yeah? Because now we can get a CE label, so it's able to sell easier. And that was the problem previously with a lot of countries where they said that they're not allowed or things like that.
I see.
It's also actually talking about Mark Spiller. I've also got a question to him. Because on that case, Mark, did you also, in Ostara, we did trials on struvite, yeah? And also when you granulate it, in the normal granulation methods, you use heat, and we saw some differences in the modification of struvite. Did you ever look at that in the trials?
Which granulation do you now mean?
No,
After,
if you would use struvite as a raw material in the granulation for some others, Yeah, we've seen that in our case, when you use temperatures or higher temperatures, it starts to modify the struvite. Did you ever did trials on that, or did you look at that at your case?
Yes, indeed we did. I tried to get this out into the public at the moment. So yeah, we did use struvite as a raw material for regranulation of a complex fertilizer. I think that's what you're referring to. And indeed, many of these granulation processes involve heating the struvite, and indeed we see that then we transfer the struvite crystal. We lose first the water and then the ammonia. Or the ammonium, which then becomes ammonia, and it changes completely the structure. We get mainly amorphous components, and we see very clearly that it makes the struvite, so to speak, worse. It becomes more amorphous, less soluble, and the properties completely change. We are going from struvite to something else. So it is not, it's actually wrong then to still refer to it as struvite, but it becomes purely a P source that then needs undergo, to my mind, more refinement. So yes, we did it. I haven't got it out, but my conclusion is broadly that this fundamentally changes the mineralogy of struvite and not to the better.
I'm looking forward to your report then.
Okay, I will share it with you first of all.
Thank you, Mark.
Okay, thanks. I'd like to move from struvites. We have some questions on the biostimulants directed at Christine. So the first question we have in is, how safe are the biostimulants for the use in agriculture? And how would you address or improve the competition of added microorganisms with the native microbiota of plants? Christine, can you help us?
For the first question about the safety, of course, we took this it was a cut-off criteria for the choosing of the microorganisms. And as you know, there are huge lists that are looking if microorganisms are toxic or not in every country. Unfortunately, they are not used for the regulatory affairs. So we have a lot of biological work done, and they are registered, the microorganisms in these lists, that they are harmless and non-toxic. But there has to be done a lot of work. We have all the tools, but the legislation, unfortunately, has not implemented yet these microorganisms. Of course, we have the responsibility to have a look if they are the good ones or the bad ones. But I think we know so much from food and feed industry, which genera are harmless. So I think we have not to be over worried about microorganisms. I think we know a lot which ones we should not use, the ones that are known in the clinical context, and why not? I do not understand. We eat a lot of microorganisms each day. We have a lot it on our skin, and it's known. And I do not understand why we think so much about that they may be toxic.
Okay, thanks very much.
And the second, could you repeat, please?
Yes, it's how do you improve the competition of added microorganisms with the native microbiota of plants?
I think at the moment we know some pieces of the puzzle, how the mode of action are of our microbes. We put in combination or use it for agriculture. But of course, you have to test a lot. Best is to go to field and try which ones are the best ones, because from our experience, it's very difficult to I'm missing the word, to extrapolate from field from greenhouse trials or from the laboratory to the field trials. But after years of testing, of course, you know which genera are the ones where you have to look, and which ones are the ones that are good to use for industry production. So yeah, you have to do a lot of testing.
Okay. Thank you, Christine. I want to know, for a matter of time, if we can keep the answer short. So I have a question coming into Renate. Why are enzymatic processes important for the bioeconomy, and are there alternatives for biodegradable coatings for fertilizers apart from lignin?
Yes, so for the first question, these enzymatic processes are really important because they replace a lot of processes that have fossil-based components. For example, processes that use organic solvents. There is a lot in this area that's already working, like degradation processes for plastics, and also these natural polymers. Concerning the second question, it's actually nice to say, no, there is not only the possibility of lignin or technical lignins out there, but also, for example, the use of plant oils, esterified plant oils, like of Kadun, that are able to do coatings, and it is, I think, very important to have these different options, because this means we have different coatings with different properties, which is beneficial for what we want to do in, for example, for fertilizer coatings, because you don't want the same properties in every coating.
Okay.
Which sounds very interesting, Renate, because I've been working for ICL, which has been a coating company. So having these natural coatings is going to be a real plus on the future. Specifically also with the new fertilizer regulation, where there is a law coming up that you need to break down the coating so many months after it has been, after its normal use. So, and I think that's one of the bigger problems in the moment with the current coatings.
That's true, because a lot of them are fossil-based. So these are one of the biggest issues for the microplastics that we have in the soil, also with nanoplastic problems, that we even have the plastics in the food chain. So yes, I'm looking forward to having this area maybe more funded and having more options to do research in this area.
Okay. Although lignin per se maybe also has a long half-life, no?
That's true, but it is not acting like a microplastic. That's good thing
true,
about
but the
it.
legislation must consider this aspect probably as well.
Yeah, but I think in legislation it's more the half-life of the carbon. I'm not sure. I need to check that.
Yeah.
Thank you. One question I have to Kari, if you can, it's a fully loaded question. Perhaps we can look at reducing the answer to a Finnish minimum. But can you give us a best case estimate or scenario of how recycled fertilizers will be made to replace imported fertilizers? In 2 sentences, please, Kari.
Well, we recently published this study where we, for example, like phosphorus fertilizers, it shows that in Europe, in croplands, roughly 72% had such a high P concentration that there is no need for phosphorus fertilizers at all. In croplands, this share is roughly 57%, and where the actual fertilizers is needed, these nutrient-rich side streams can replace roughly almost 90% of the fertilizing requirements. So there is a great potential with these side streams to replace mineral fertilizers.
Excellent. Thank you. I also have a question to Martin. Will samples of the siderophore be available? I guess there is already a business interest on this. I guess what we, whoever wrote this, please, we can contact us and we'll lead you through to Martin. Martin, there you are.
Yeah, so for sure that there is a possibility you can reach out to us and we can discuss, but it is very important to know that when testing the samples, a formulation needs to be done, and efficient formulation has to be done. So the best is to come to us and discuss, and we can see what we can do, and I'm sure we can do something.
Thank you. Then I have a question for Günther. We've been talking about solutions using microorganisms and biostimulants. Are we going to have the same conversation in 20 or 30 years?
Well, I was asked to give a short answer to that.
Indeed.
I could spend hours now talking, but let's say I think we need to have a transition to get to a more circular economy. So we probably have a discussion on develop things further to replace some aspects or to change some aspects, but I don't think we will have the general question as it is now. At least I'm optimistic.
Okay, good. That's the right answer. No. So we're slowly coming to the end of it. I just wanted to ask a question to the three panelists here. And so we've seen all these changes. So one thing is like, where do you expect in a sentence, where are we going to be in your field in 5 years? Also, one sentence, Robert.
The thing of two sentences.
Two sentences. Good.
The issue with phosphorus, I'll talk about phosphorus here, is that phosphorus is on the critical raw material list. But the European Union introduced this year also a strategic raw material list where phosphorus is not on, which means that you can be on the critical raw material list, but you still don't get money to develop the phosphorus recycling further. You need to be on the strategic raw material list. So that's where the ECP at the moment is working on to get that on that sub-list, which is more important. So that's where we believe in 5 years we need to be on there in order to get, because Europe doesn't have phosphates, to be on that list to make sure that there are enough investments to get phosphorus recovery and to make it into a useful product.
Excellent, thank you, because you actually answered the second question, if you had one wish. So your wish has been taken. Thank you. Renate, please, where do you see your field of the lignosulfonates in 5 years? And if you had a wish that I could fulfill, what we could do?
I really hope that in case of the lignosulfonates, we come to a point where we can replace a lot of fossil-based materials in that area, because there are a lot of prototypes out there. And also our working group is working on a lot of stuff that's very interesting. So I hope with the good luck with the funding and maybe some company partners, we will be able to show actual new products in 5 years.
Nice. And Günther, please, words of wisdom.
Well, thanks. I think, of course, there will be changes in legislation and there will be novel products coming, but I think what really needs to be done and will be done in the very near future is to take into account, also Kari pointed to that aspect actually, that a specific and more precision farming initiatives and digitalization in helping to precise application of needed microbiomes and needed biocontrol solution must take place and will take place. And also, I said it just in a sentence, microbiome. That sounds like of course, this is also a new aspect. Microbiome is more than a single organism. So to shape those will be also a future aspect, which will be coming up in the next years, I'm sure.
Thank you. And then, even though I haven't asked myself, what I see in 5 years, I hope to see, and it's a little bit my wish, I have two wishes. I hope to see some of our products on the shelf or in big bags or on pallets that make their way to sustainable agriculture. And so that's kind of my wish, that this bears fruit and is implemented. The other wish I have is that you join us in our next seminar. But before you do that, I just wanted to show you when we started off about 2 hours ago, we started off with one of our fertilizer solutions, which are our Nutri-Gels. These are compacted with microorganisms and struvite. We added water, and 2 hours later, we have our hydrogel. So this is a slow release, water absorption, slow release of nutrients, and slow release of water. So this is the demonstration of one of our solutions that we've created here in SUSFERT. And then if we can pop up the presentation, there's more to come. So the best is yet to come, so to speak, when we take our components that we have demonstrated and shown here to the next level of looking at what do we do with the products and what impact do we hope to achieve with our products. And so here you have the opportunity to dial in again. This is in September 27th, as you can see. And the nicety of this is a real hybrid event in Vicenza. We have field trials in Vicenza. We invite you to come down. Details will be made available on our website shortly, so you can join us. It's a stakeholder event with numerous actors within the value chain, not just Team SUSFERT, but other experts. Our advisory board will be present. So please note that, come to our website and find out how to best get there and register for this. Otherwise, you can join us online. In addition, we have a number of proactive and engaging grassroots mobilization events planned throughout every country where we've done our field trials. We're kicking off very soon in June with 2 events in Austria. That will be followed in France, another Austrian event, and we will have an open day in Berlin at Habitat. Then you can see and witness our results also at AFIP in Rotterdam. And then we invite you to our final conference in November as the project comes and nears its final months of conclusions. So more details of that to come online. So with that, I want to thank you very much, and thank you for joining us. Hope to see you again. And thank you specifically to our presenters and to our panel. And hope to see you all soon.
Thank you.
Thank you. Thank you.